I think so. It is now getting recorded. I think so. Is my screen sharing, students? I think it is still sharing. Okay. So I'll go to the full screen mode. So the topic which we are going to see today is fundamentals of error correction and error detection. So which is most probably um, given by the error control codes. So this is what we are actually planning to see today. So fundamentals of error correction means actually we this is more or less going to be getting related with the digital communication system. So if you look into a digital communication system, you'll be having the block of channel coding. So in channel coding, you'll be having the concept of error correction and detection. Okay, so error correction in the sense once when you transmit a binary 1 or 0 into a channel, so there is a possibility that due to the presence of the channel conditions, inter-symbol interference, and the noise situation in the channel. So there is a possibility of binary 1 getting changed into a binary 0 or a binary 0 getting changed into 1. So we need to detect errors. So we need to detect errors. So we need to detect errors in the sense that the errors have to be minimized to a certain extent in the transmitter itself, and also in the fact that a controlled amount of redundancy needs to be added in the channel. So controlled amount of redundancy adding is nothing but channel coding. So thereby where you can minimize the addition of errors in the channel. So error correction and error detection, they can be done by using error control codes. So we'll be seeing fundamentals of error correction and error detection, so which are given by the error control codes. Okay. So as I said, fundamentals of error correction. So you'll be having the main concept of the digital communication system, or any wireless transceiver. You'll be having the channel coding scheme. So this channel coding is also referred to as error control coding. So mainly channel coding and error control. So channel coding is mainly used to improve transmissions. So transmissions in the sense you can have transmission in the sense you can have controlled amount of redundancy in the channel. Okay, so what I would say that improve transmissions in the sense, so improving controlled redundancy. So that is adding controlled redundancy. That is what you can have. Controlled redundancy. You can have a controlled. You can have a controlled added controlled redundancy. So before being transmitted, this is what you can say. This is what you can be say. So so channel coding is mainly used to detect and control errors. So that is you are adding a controlled amount of redundancy. So redundancy means that is the certain bits which are of less significance or of less importance, less significance or of less importance. That is what I can say. So channel coding, it changes information into a suitable form of transmission. So with concepts on reliability, enhanced reliability. So I'm mainly adding redundancy. Adding redundancy, it allows for information restoration or recovery when needed. Okay, or recovery when needed. So redundancy, you can have either to come as a set of useful information bits, so which are less significant, when it goes into the channel for transmission, and when you decide out in the amount of bits in the receiver. So you can have control redundancy in as channel coding, and also so you will be having redundancy in source coding block also. So in source coding, if you have Huffman coding and channel funnel coding, so it will result in removing unwanted information bits. So that is redundancy. So redundancy will be prevalent when you are going for source coding and also the channel coding, which we are just seeing now. So it ensures a proper transmission quality. It ensures proper transmission quality. So transmission quality, the main metrics are bit error rate. So if you look into the physical layer, channel conditions, it is bit error rate. So this is a bit rate quality, that is bit error rate, or that is the packet error rate. Okay, so PER. So bit error rate, it is with respect to the network layer terminologies, and bit rate is with respect to the physical layer terminology. Okay, so this is the well-known block diagram of the channel coding. I mean the digital communication system, where with it is with the emphasis on channel coding. So the amount of information bits, the amount of the amount of information bits to be transmitted, mm, the amount of information bits to be transmitted will be passed into a source coder. The amount of information bits will be passed into a source coder. So the source coder mainly it is used to remove redundancy, unwanted or insignificant bits. So whereby you can use Huffman coding or Shannon-Fano coding. And the topic of discussion for today is channel coding. The topic of discussion for today is channel coding. So channel coding is nothing but it is actually going in for controlled redundancy. So error control coding. So mainly you'll be having error detection and error detection. Okay, so then afterwards you can just modulate the information data bits by using a carrier, and you can transmit, and in the receiver chain you will be having all the reverse process. So the concept of channel decoding. So the channel decoding, you need to do all the reverse process. So coding can be either by using the form of a blocks or a bit by bit representation. And in channel decoding you'll be having the reverse process. If you use convolutional encoder in the transmitter section in channel coder. So in channel decoder, for example, Viterbi decoder, so you'll be able to do the reverse process. Okay, and also source decoding. So the important performance metric for any digital communication system here will be to minimize the error. So error rate, bit error rate, symbol error rate, packet error rate, it needs to be minimized. That is what it is being done actually. Okay, so the mainly channel coding, as we have been discussing for the session. Channel coding includes error correction and error detection. So as you know, information data may be corrected during anywhere during the transmitter section. Information data may be corrected anywhere during the transmitter section. So for reliable communication, errors must be detected and corrected. So reliable communication refers to error detection and error correction. So error detection and error correction, they are either implemented either at the data link layer or at the transport layer of the OSI model. So error control is actually error detection, and also it is error correction. So you need to transmit the redundant data. So you need to transmit the redundant data so as to allow the receiver to recover from all the errors by itself. So no sender retransmission is required. Okay, so repetitive transmission is not required. Thereby you can minimize the that is, you can have power control. Okay, so you can have efficient amount of data bits to be transmitted into the um, into the wireless channel, and depending upon the components of the receiver you can just detect them. Okay, so this is the scenario of the the digital communication system, and this is the fundamentals of error correction. So we'll pass on further to the types of errors. So errors may be either it might be due to a single bit errors might be either due to a single bit error, or it might be more than one bit, multiple bit, or burst, or a group of bits, burst errors. So single bit errors and burst errors are mainly used in serial transmission. So serial one by bit transmission, they arise due to single bit transmission or a group of bits transmission and so on. So most probably these errors are prone to in serial transmission. Um, so so the situation is that so you can have a single bit, multiple bits to be prone to errors or burst errors. Now consider here this scenario, it is given for your easy understanding. See here, these are the send bits, for example 00 0 0 0 0 and 1 0. So these 8 bits are given here are transmitted. So these 8 bits, so these 8 bits are transmitted, and these 8 bits are received. See, here in this case, when you transmit the information into the channel, when you transmit the bits into the channel, so that there is a possibility that this particular bit, so this fifth bit is getting changed into another form. So that is the bit binary bit 0 in the fifth position. It is getting changed into binary 1 in this fifth position. So 0 is changed into 1. So a single bit is subjected to error in this particular group of binary bits transmission. So you can, if you transfer these set of bits, these 8 bits, so the fifth position is prone to error. Likewise, you'll be having the second case. The second case in the sense, I mean, the second case in the sense, it is that is the multiple bits error which are prone to errors, or you can have the um, what to say, the more than 2 bits are also prone to error. More than 2 bits are also prone to error. See here in this case, so a group of bits are sent actually. So a group of bits are sent, and and another scenario is that, for example, these bits, these 5 bits are prone to error. See, 0 gets changed to 1, 0 gets changed to 1, and vice versa. So 1 gets changed to 0, and vice versa. Okay, so these bits are sent, and it is received actually. So probably you can expect questions in GATE exam. So what is the bits amount of bits which are prone to error in case of a single bit error transmission, or a multiple bit error transmission, like in this case? See here, the second bit in this particular packet, or in this group of bits, is changed to 0. Likewise, this bit 0 is getting changed to 1. So here two errors, multiple bits. So this is what is given: multiple bits are prone to error. This particular case, two errors. Then this is the burst error scenario. Then this is the burst error scenario. So you can easily understand so how errors get changed. Okay, and based on this, you can just find out what is the bit error rate. For example, if you want to calculate the mm, if you want to calculate the bit error rate, no, so you need to compare the number of bits which are prone to errors, the number of bits which are prone to errors in comparison to the transmitting and received bits. Okay, so mainly you need to detect the errors. So error detection means you have to decide whether the received data is correct, or without having a situation to retransmit a copy of the original message. So you need to detect errors, what are the amount of errors in that particular case, and you need to detect the amount of errors in that particular case. And the error detection, mainly it uses the concept of redundancy, which means that adding extra bits for detecting errors at the destination. So this is the case. So this is what we are seeing earlier actually. So you can detect errors, for example, in this particular case. So if you want to find out the bit error rate, for example, see, for if we consider a transmitter, if we consider a transmitter, so we have these 5 bits, 1101. Okay, so let us have these 5 bits, so 10110. And in the receiver, let us say that this particular 0, 0, it gets changed to 010. So if you compare this, so when you compare or if you want to find out the bit error rate, so what is the bit error rate? What is the bit error rate for what is the bit error rate for a particular system where it transmits 10110 and receiver 1000 and 10? So if you want to find out the bit error rate, so number of errors comparing number of errors comparing transmitting and number of errors comparing transmitting and receiving bits, number of errors comparing transmitting and receiving bits, and receiving bits to the total number of bits. the total number of bits. Okay, so if you want to calculate the bit error rate for this particular system, let me say that BER. So this particular BER is nothing but, so you see here you have 5 bits. Yes, so here you have 5 bits. So 5 bits, and the receiver also you have 5 bits. So if you compare these 5 bits, see the first bit is initially transmitted as 1. It is received in the channel as 0. So there is a difference, one error. Then you have the second bit. So 0, it is 0. There is no change, no error. Then there is a third bit is binary 1. Then it is received in the receiver as 0. So the second bit is also prone to error. Likewise, the fourth bit, you have a binary 1 to get transmitted. You have binary 1 to get transmitted, and it is received as 1. And a binary 0 is transmitted, it is received as 0. So the error bits are, if you compare here, so the first bit is in error actually. So the first bit, if you look in here, it is in error. Then likewise, the third bit is also in error. Third bit is also in error. So the remaining bits are the same. So the bit error rate is nothing but it is 2 by 5. So the bit error rate is almost 2 by 5. That is around 0.4. Okay. So okay. So you give the bit error rate, or you can have it as 2 by 5. Okay. So bit error rate is 2 by 5. That is this is how you need to calculate the bit error rate. Likewise, you can calculate what is also the probability of error. But anyway, uh, to detect errors, you should be in a position to detect errors in a group of bits. So as we'll be seeing error control coding, the types of error control coding. Okay. So I'll go back to the full screen mode. Okay. Um, okay. Now, as we were, the important thing in this particular error control coding is that, so you'll be having redundancy. See, you have these set of bits. You have this as a set of bits. So these bits can be transmitted either by using linear block codes, can be transmitted by using a linear block codes, or you can transmit them by using convolutional codes, by using generator functions. Generator functions are polynomial either in the transform domain approach or in the time domain approach, whichever which you are aware of. Then you need to have the redundant bit, so you need to check with redundancy. Okay, so the data bits will be appended, either pre-appended or the post appended with the redundancy bits. See, the redundancy bits are getting added here. It is added at the front. So for example, if you look into any high-speed modulation scheme such as orthogonal frequency division multiplexing, so the data will be appended, so in the form of a cyclic prefix. So likewise, you can just correlate that. You can just correlate that, and you can just transmit and receive. So here you're transmitting, so you need to check at the receiver. So in case if the transmitted data is if the received data is in accordance with the transmitted data, then you can accept or reject. So this is the situation. So you're just transmitting the data, and you're just receiving the data. So whatever polynomial functions which are using at the transmitter, it needs to be used at the receiver, so that you can easily decode. So the checking function is nothing but it is the decoding or the reverse operation. Okay. Okay. So the error control codes. So the error control codes. So as you know, it is used for error detection and error correction, correction, and it introduces controlled redundancy to prevent noise in the channel. Okay, so there are various types of error control codes. So probably in, block codes, cyclic codes, convolutional codes. In addition to that, you have Reed Solomon codes, BCH codes, turbo codes, and so on. Okay, so probably these three codes are nothing but what is most predominantly predominant. So you can just go through these codes, and you can expect problems or questions based on these particular codes. Okay. Okay, so for any particular block codes, any error control codes, whether it is block codes, cyclic or convolutional codes, so this following setup needs to be uh, uh, considered. This following setup needs to be considered. So that is you'll be having the transmitter receiver, sender receiver. So you'll be having the input data bits. So you'll be having the input data bits, uh, k data bits, the data word generator or the code word. So how to generate these code words? It depends upon the processing scheme which we are going to consider. Okay, so if you take k bits as input, so if you take k bits as if you take k bits as input, so the k bits are taken as input. They are constructed into blocks. They are constructed into blocks. They are then appended with the mm, what to say, the generator polynomial. They are just appended with the generator polynomial, and then the code word is found out. So k bits are given as input and n bits are taken as the output. So this is nothing but always the channel is considered to be unreliable. The channel is considered to be unreliable, and in the receiver you need to have the reverse process of everything. Okay, so you have to pass the code word, so you need to consider the reverse process. So yeah, the checking is nothing but it is the polynomials which are going to use the decoder, and then you need to find out once again what are the information bits or the data which is being transmitted and received. Okay, so this is the situation. Now here we'll go on to the first possibility of we'll go to the first possibility of linear block codes. So you see here k bits are taken as inputs. So if it is an n comma k linear block codes, k bits are taken as input. So the fundamentals which are required for constructing linear block codes is that. So in this session we are seeing the fundamentals of linear fundamentals of error control codes. That is, the first code is a linear block code. See, so the message vector. So it is a k by 1 message vector is given to be m. So as you know, the code word is nothing but it is C is equal to M into G. C is equal to M into G. C is equal to M into G. So the size of the code word is nothing but 1 by n. Then the error vector is also 1 by n. So so you have n outputs. So k bits are taken as the input, and n bits are taken as the output. K bits are taken as the input, and n bits are taken as the output. So the received vector R is nothing but it is the C code word plus error vector. So depending upon the length of the code word, depending upon the length of the code word, the error pattern will also change. The error pattern will also change. Likewise, the generator matrix. So generator matrix. So generator matrix is G. Okay. Then you have the parity check matrix. The parity check matrix. So the dimension of the parity check matrix is actually the dimension of the parity check matrix is actually uh, n cross n minus k. So the n minus k, or it is nothing but m by n. You can have it as m by n. So m is nothing but the number of parity bits. Okay, then syndrome. So for error correction and error detection, you need to know the syndrome. So S is equal to R into H transpose, which is equal to E into H transpose, which is 1 cross n minus k. So E is the estimated error vector 1 by n, and E is the he cap, and that is C cap is the estimated code word, and M cap is the decoded message vector. Okay, so if you just look into the block diagram based representation, if you look into the block diagram based representation, so m bits are given as the message vector. So m bits are considered as the message vector here. Then you have the generator polynomial. When you just multiply um, m into g, when you just multiply m into g, it becomes the code word. It becomes the code word. Then it becomes the code word, and then then you can just find out what is the received code word. You can just find out what is the received code word. So the received code word is nothing but it is R is nothing but as it is written here, C plus E. So C plus E. So here it is a modulo 2 addition. So wherever we have this error control coding concept, we will be having the process of modulo 2 addition. We'll be having the process of modulo 2 addition. So R is equal to C plus E as it is written here, code word plus error. So this error you'll be having depending upon the number of input bits, the error pattern will change. The error pattern will change. Um, then you need to calculate what is the syndrome. Syndrome, as you know, is nothing but the received code word with the error and H transpose. So the transpose of the parity check matrix. Syndrome is nothing but R into H transpose, or the error pattern E into H transpose. Okay, so you'll be having the error pattern generation. Depending upon the length, the error pattern will change, where it is going to be linear block code or it is going to be a Hamming code. Okay, then you can find out what are the estimates. You can find out what are all the estimates actually. So G inverse, so this is the inverse of the generator matrix. Then you can find out what is the decoded message vector. Okay, so this is the basic fundamental concepts which you need to be aware of linear block codes. So if you are aware of this, you can easily solve problems using using a linear block codes. So most probably you will be expecting in competitive examinations like GATE exam. Okay, okay. So in a linear block code, so uh, the exclusive or modulo 2 of any code words is another valid code word. The exclusive block code is another any other valid code word. To guarantee the detection of up to S errors in all cases, the minimum distance in a block code must be d min is equal to S plus 1. So the minimum, you need to calculate what is the minimum distance. So minimum distance is nothing but S plus 1. Okay, so in a linear block code, always the operation is that, so you'll be having either modulo 2 operation, or it is nothing but it is an exclusive OR operation. Okay, now for example, if you consider this particular linear block code, if you consider this linear block code, uh, if you consider this linear block code, so this is the 7 comma 4 linear block code, which is so given by the generator matrix. So 7 comma 4 linear block code. So this is n comma k. Okay, this is n comma k. So for instance, so this is n comma k, where n refers to the number of output bits. N refers to the number of output bits. For instance, so probably I'll try to let you know here. Okay, so for instance, so if it is, for example, if it is a 7 comma 4 means, so this is actually an n comma k code. So this is an n comma k code. So so n comma k code. So this is an n comma k code. Uh, n comma k code. So this is, which implies so that is n bits are output. N bits are output, and k bits are n bits are output. N bits are output and k bits are the input. And if you want to know what are the parity bits, okay, so the parity bits, want to know what are the parity bits. Parity bits is nothing but it is m is equal to n minus k. Parity bits in m is equal to n minus k. So for here instance, the number of output is equal to 7. Okay, n comma k. So this n comma k is nothing but this is, as it is given in the problem, as 7 comma 4. 7 comma 4. The k bits are given as input, 7 comma 4, and k bits are given as input. K bits are given as input. Okay, so this is 7 comma 4. So obviously the parity bits will be 7 minus 4. The parity bits will be 7 minus 4, which is equal to 3. So 3 parity bits will be there. So okay, so now the generator is given such that, now from the generator you can find out, so as you know, the generator matrix is nothing but it is a combination of the identity matrix. It is a combination of I matrix and the P matrix IK, and so generator matrix. So you can find out what is the generator matrix. So the generator matrix is nothing but it is an identity matrix. It is made up of, is nothing but it is IK. Okay, so this is its dimension. We have seen the syntax of the generator matrix. Okay, generator matrix is nothing but it is k by n. So the syntax of the generator matrix is k by n. So it is made up of this identity matrix k, I suffix k. It is ik, and it is concatenated with along, and it is concatenated along with the parity matrix. Okay, so parity matrix is nothing but it is another n by k matrix. Okay, and concatenation along with the parity matrix. The parity matrix. So here, for instance, now if this particular, so if it is, for instance, if the message is given as 1001, as you know, for instance, if the message is given as 1001, the message is given as 1011. So 4 bits are given as input. So 4 bits are given as input in the sense. So there can be 16 combinations, as you know, 16 combinations. There can be 16, or I can say that it is 16 possibilities. It is 16 possibilities. So according to the binary coded decimal, starting from 00000, comma, what else I can say, 000, 000. So then you can have likewise 00001, and up to what I can say is up to 11111. So these are the possibilities which I can have. These are the possibilities, and these are the possibilities which I can have. So all one. So set of all possible ones. Okay. Um, a set of all possible ones. So 16 possibilities, as you know. Now, based on these 16 possibilities, you need to find out what are all the what to say. We need to find out what are the possible code words. So here the generator matrix is given. So if you want to find out what are the corresponding code words, see here it is given here. If the generator matrix is given here, um, the generator matrix is given here. So if you want to just find out what is this, so you have to just multiply. You have to just multiply, and always you need to perform modulo 2 addition. So this is m into g. So this is nothing but you have to just multiply. Uh, you have to just multiply. Okay. So you have to just multiply this. For example, in this problem, if we consider 1011, 1011, 1011, then you have to just multiply along with the generator matrix. So you have to multiply this 1 by 4 1 by 4 um, 1 by 4 vector along with this 4 by 7 matrix. So you'll be getting a 1 by 7, that is 1 by n. So the size of the code word will be C is nothing but 1 by n. So C is 1 cross n. C is 1 cross n. Okay, C is 1 cross n, in accordance with the what we have seen here. C is nothing but 1 cross n. So I'm just trying to correlate you what is the fundamentals of this linear block codes along with a particular commonly used problem. So these sort of problems you can expect in GATE exams or any competitive exams which you are going to prepare. Okay, so you can find out the code words in this particular fashion. So if there is no error, then the received code vector x will be equal to c. So the received code vector will be x is equal to c actually. And so you find out what is the syndrome. Syndrome is nothing but it is r into h transpose. So r is nothing but it is a received code word plus the error pattern. Received code word plus the error pattern. Okay, so here let's see suffer an error such that the received vector is nothing but x is equal to c modulo 2 or x or e. So for example, so see here the error pattern is such a way that c is equal, e is equal to 0010000. So here in this case the the error is in considered to be in the third position. The error is considered to be in the third position. So you have the corresponding code word. So you have the corresponding code word. See, the code word is taken from here. So you have 101. So you have 10110001. Then you have 101110001, and here you have 101101. So you just perform modulo to addition here. So you just perform modulo to addition or XOR operation. So as you know, XOR operation is nothing but, so for either all lower or all higher values, you'll be getting 0. See, and therefore 0110, you'll be getting 1. Okay, so if you XOR 1 and 0, it is going to be 1. So 0 and 0, it is 0. Likewise, if you do this operation, you'll be able to get what is the received vector R. Then you can calculate what is the syndrome. Now the procedure to calculate the syndrome. So S is equal to R into H transpose. S is equal to R into H transpose. So R you have found out from here. S is equal to R and H transpose. R you have found out from here. So H transpose, H is already it is being found out here from the generator matrix and the proper structure. So H matrix is nothing but it is the parity matrix concatenated with I. Parity matrix concatenated with the I. So you'll be able to get what is the um, H matrix. Okay, so you'll be able to get what is the H matrix. So the received code word. So S is equal to R into H transpose. So 1000101, and if you just multiply, and if you just multiply along with the parity check matrix, so you'll be able to just get the syndrome like this. So see, the syndrome in this case is nothing but, 1001. So 101. So 101, if you look into the error pattern, so if you look into the error pattern, the error is in the third position here. The error is in the third position here. The error is in the third position, and also you have 101. So 101 is the third position. So error is in the third position. This is how you can detect errors. This is how we can detect errors. Okay. So error detection is nothing but it is error detection is nothing but, so how to detect errors by using linear block codes. Okay, so if you look into the error pattern, if you look into the error pattern so if you look into the error pattern the error pattern if you look into the error pattern. Okay, if you look into the error pattern, so the error pattern, so you see here, this is an n comma k linear block code. So this is 7 comma 4 linear block code. So 7 comma 4 linear block code in the sense. So the output will be 7 bits. So error pattern. So the error pattern will also be 7 bits. So you can have, for example, 1000 10000. So 1 2 3. Okay, so 7 bits. So error in the first bit, or you can have error in the second bit. Error in the second bit. Uh, 0 0 0 0. Okay, 0. Okay, so this is error in the first bit or error in the second bit, 0 1. Okay, so this is error in the second bit, or you can have error in the third bit likewise. So error in the third bit. um, okay, so and so on. So likewise you can have error, and so this corresponds to error in the third bit. Error in third position. Okay, this corresponds to error in third position. This corresponds to error in the third position. So this is what it is being given here. This corresponds to error in the third position. For instance, for example, so error in the third position, and specifically you can say that um, error is lying here. Error is lying here. So error is lying here. This was what we considered here. This was what we considered here. Or for example, if we just uh, or if we just make it more easily understandable. So the error is in the third position. So error is in the third position. Error is in the third position. See here also we have considered while calculating the error in the third position. So here see the syndrome S value. The syndrome S is equal to R into H transpose. So 101. So this is E1, E2, E3, E4, E5, E6, E7. So this is 101. So 10 is in E3 position. So 101 is in E3 position. So thereby you can have this. So probably I'll so this you can just do it easily. Okay. So you can find out where this is a procedure to detect the errors by using syndrome. We are just we by using syndrome we are just detecting errors. Okay, then we have seen how to detect errors. Likewise you can also correct errors. Okay, for instance detection of n comma k linear block codes. So error detection is easier than error correction. Error detection is easier than error correction. So the detectable errors, it is given as 2 power n minus 2 power k. 2 power n. How to detect errors? Okay, how to detect errors in this particular position? Then the correctable errors. So these are correctable errors. So correctable errors are 2 power n minus k minus 1. So which are non-zero syndromes. So you can have all these. Okay, so uh, the next thing which you need to be aware of is that the Hamming distance. The Hamming distance. Okay, so the Hamming distance. So Hamming distance between two words is the number of differences between the corresponding bits. So Hamming distance. So Hamming distance, Hamming weight. So these are all some parameters related to code words. Okay, Hamming distance, probably we'll be seeing problems in the forthcoming slides, how to calculate Hamming distance, Hamming weight, and Hamming distance. Then also like Hamming distance is the smallest Hamming distance between all possible pair of code words. Likewise you can have Hamming weight. Okay, so you can have Hamming weight. Likewise Hamming weight is also there. So Hamming weight is nothing but non-zero elements in C. Likewise, you can just have non-zero elements in the code word. So non-zero number of non-zero elements in the code word is nothing but number of non-zero elements in the code word. Number of non-zero elements in the code word is number of non-zero elements is the code word. Likewise, Hamming distance. So Hamming distance, Hamming weight play a major role in error detection and error correction. Okay, now we'll pass on to this particular problem. Uh, okay, so find the Hamming distance between two pairs of code words or words. Okay, so calculate the Hamming distance. Calculate the Hamming distance between two code words. See, for example, you have these code words 000 and 011. See, if you compare these two bits, see, for example, if you compare these two bits, see, your first bit is 0 and the second bit is 0. Okay, so there is no change. So the first bit is 0, the second bit is 1, there is going to be one change. So up to now the Hamming distance is 1. Now the third bit is 0 and the third bit in the next code word is 1. So the Hamming distance increases to 2. So the number of Hamming distance is nothing but the distance between two code words. That is the number of differences in which differ in position between corresponding bits. Okay, Hamming code words. Likewise, if you take into the second problem, if you take the second problem, uh, calculate the Hamming distance between the code words 10101 111110. Okay, see, if you compare these three bits, I mean if you compare these three bits, you have if you compare these three bits, so if you compare the first bit 1 and the second bit 1, so there is no change. Okay, there is no change. Then if you compare the second bit and this second bit here in this code word, there is one change. So the Hamming distance is as of now 1. As of now it is 1. Then if you compare the third bit, if you compare the third bit and if you compare the third bit in the second code word, it is 1, so there is no change. So there is, as of now, there is only one Hamming distance. Then the fourth bit is 0. The fourth bit in the second code word is 1, so there is a change. So the Hamming distance increases to 2. Hamming distance increases to 2. Then if you look into the last bit, it is 1. If you look into the last bit, it is 1. And then if you look into the last bit, it is 1. Last bit is 1. And then the next last bit is in the last bit in the second code word is 0. So the Hamming distance increases to 3. So see, the answer is 3. The answer is 3. So I'm just giving explanation for how to calculate the Hamming distance. So you can expect problems in GATE exams on how to calculate the Hamming distance. Hamming weight is also there. So this is Hamming distance is 3. Okay. Okay. Now here we'll consider this particular problem. A linear Hamming code is used to map 4-bit messages to 7-bit code words. Okay, the encoder mapping is linear. If message 0001 is mapped to the code word 00001111 and the message 0011 is mapped the code word 1100110, then the message 0010 is mapped to. So you need to find out what are the possibilities. Okay, see here there are two messages given. There are two messages given and there are two code words. See, the message 1 is mapped to this code word M1 C1. So M2 C2. Okay, M2 C2. They're asking what is the next possibility. Okay. Okay, see, you have to make sure of the properties of the error control codes, linearity property. Likewise, if you're going for a cyclic code, it is a, a cyclic, I mean, so cyclic shift property. Okay, because the sum of two code words, two linear code words, is nothing but is another linear code word. So that is what the property is satisfied. So you have to use this. Okay. So see here, message 1 is written here. Message 2 is message 2 is written here, and no, code word is written here 00001111. Then code word 2 is written here. So by employing the property of linearity property of a code word, okay. So please be aware of the properties. So if you add these properties, so here, as you know, addition. So as you know, addition is nothing but it is a modulo to addition, or it is nothing but XOR operation. Modulo to addition operation or XOR operation. Okay, so this is modulo to operation or XOR operation. Okay, so modulo to operation or XOR operation. So if you just add 2, so this is, see, 0001. And then this is 0011. So if you just add, you'll be able to get the message 3. See this property. So these two messages 0001, and this is logically XORed modulo to operation 0011. So 0011. So if XOR 11, it is 0. So 01 according to XOR table. So different combinations. So it is 1. So all low possibilities or higher possibilities, they are 0. See, 00 XOR 00 XOR is 00. So this is 0. Likewise, the code words will also be like that. The sum of two code words will result in another code word. Okay, XOR of two messages will result in the next message. Likewise, sum of two code words will also result in another code word according to the property. Okay, so so this is nothing but okay, 000011 and 1. Then if you XOR, see, if you XOR this 10, it is 1, 11. So it is a similar possibility. 11, it is 0. So 11, it is 0. So 00, it is 0. 00, it is 0. So likewise, 01, it is 1, and 01, it is 1. So this is the resultant code word. So see here, this problem, see, message 1 is mapped to this, message 2 is mapped to this. So we are adding these two messages, we are getting this. So we can easily decide out that by using this property you can find out the answer. So 00110, then these two code words, so it is resulting in 11000001. So the option is given here, this is nothing but D. So the D option, so 11000001. Okay, so this is the problem. Then next thing is that the next type of linear block code is nothing but cyclic codes. Okay, so cyclic code is also a linear block code which uses a shift register. Cyclic code is also a linear block code which uses a shift register to perform encoding and decoding. Okay, see, linear block codes can be processed by using in the form of blocks parity bits. So cyclic codes, in the sense, it will be represented in the form of polynomials. Cyclic codes, it uses a shift register to perform encoding and decoding. The code word with n bits is expressed as, the code word with n bits is expressed as c of x is equal to c1 x power n minus 1 plus c2 x power n minus 2 up to cn. So c suffix I is nothing but either a binary 1 or a binary 0, and these are nothing but the polynomials. Okay, so in general, okay, so in general the code word is nothing but it is m of x into x power n minus k plus c suffix p of x. So the c suffix p is nothing but it is the remainder. C suffix p is nothing but it is the remainder which is obtained by dividing the product, which is obtained by dividing the dividing the product of the message signal m of x. That is the message polynomial. Always m of x is refers to, m means it is a message, and this m of x is nothing but message polynomial, um, x power n minus k, um, by generator g of x. If the received signal is c of x plus e of x, where e of x is the error, where e of x is the error signal. Okay, so to check if the received signal is error free, the remainder from dividing c of x plus e of x by is obtained, then it is going to result in the syndrome. See, so syndrome, this syndrome is more or less similar to this syndrome is more or less similar to what we actually have seen in the linear block code. See, syndrome here, S is equal to R into H transpose, which is equal to E into H transpose. S is equal to R into H transpose, um, plus E into H transpose. This is similar to the one which we are using in linear block codes. Okay. So if 0 is received, then the received signal is considered to be error free, else from error pattern is detected from the known error syndromes. Okay, so cyclic codes, they will be so cyclic codes, as we have seen, it is more or less similar to the linear block codes, but only the fact that it will be represented as polynomials. For example, the error pattern. So error pattern which we have seen already here. Okay, so error pattern is nothing but, for example, so probably I can also convey here. So error pattern, for example, if it is going to be an n comma k, so if it is going to be an n comma k, if it is going to be a 7 comma 4, it's going to be a 7 comma 4 means, for example, e1. So for example, error pattern 1 is equal to 1000 000. So this is a 7 bits are output. So error is in the first bit, error in first position. And likewise, if you say e2, if you say e2 if you say e2, so this is nothing but 0 1 0 0. So this is error in the second position. Error in second position. Likewise, error in the second position. So E3, which we have already seen. I'm just correlating here. E3 is nothing but 0 0 1 0 0 0 0. So error in third position. Likewise, the error E4. So E4 is nothing but it is 0 0 0 1 0 0 0. Error in third position. Error in fourth position. Okay. Likewise, you can have error. So you can have a vector matrix. Okay. So error in the fourth position. Likewise, you can have error in the fifth position. So these are all the possibilities. So E5 is equal to 0 0 0 0 1 0 0. Error in the fifth position. Error in the fifth position. Likewise, you can have E6 and E7. Likewise, you can have E6 and E7. So E6 and probably I'll also try to go here. Uh, uh, so E6. So E6 is equal to 0 0 0 0 0 1 0. Error in the sixth position. And last but not the least, error in the seventh position. So this is the error pattern. E7 is equal to 0 0 0 0 0 0 1 1 2 3. So error in the seventh position. Error in the seventh position. Likewise, you can have what are the error patterns. Okay, so you can just have a view of what. So I'm just relating what is the various error patterns. I'm just writing what is the various error patterns which we have seen in the linear block code. See, we have seen in the linear block code. So this was the error pattern. So this is the error in the third position. So I wrote here up to the third position, but to be generalized, error in the third position, but to be generalized, I've just written here because cyclic code is nothing but it is more or less a linear block code, but with cyclic shift property. Okay. So cyclic codes are computationally efficient subset of linear block codes. So the generator polynomial. So the important thing is that here information will be written in the form of polynomials. So the generator polynomial g of x is nothing but summation I is equal to 0 to n minus k and gi x power I. So this is the representation for the generator polynomial where g is given in terms of the coefficients, generator coefficients, and h is the parity check polynomial h of x, and where h are the nothing but the corresponding coefficients of the polynomial. Then the constraint. So g of x is nothing but it is the generator polynomial, the parity check polynomial. So the constraint is that the multiplications of the polynomial should be equal to the input message. X is the input message, x power n minus 1. Okay. So if you want to encode a cyclic code, if you want to encode a if you want to encode a cyclic code, so c of x is nothing but it is the multiplication of the message polynomial and uh, generator polynomial. It is a multiplication of the message polynomial and the generator polynomial. So c is equal to c suffix n minus 1. So c1, c2, these are nothing but the code words, the coefficients of the code words. So this is c is nothing but once again represented in terms of convolution. So polynomial multiplication is nothing but it is the corresponding convolution of the coefficients. So the encoder for a cyclic code word can be constructed, and likewise the decoder for cyclic code can also be constructed. Okay. Okay. So the important thing is that the cyclic code words, they operate they operate by using cyclic shifts. They operate by using cyclic shifts. They operate by using cyclic shifts. So multiplication by xj modulo to x power n minus 1. So it is equal to cyclic shift left shift by j positions. So Cj is nothing but x into Cx mod of x power n minus 1. So Cj is equal to the coefficients. Okay, coefficients. So it is represented in generalized manner. Okay. So the syndrome calculator. So likewise the syndrome calculator for cyclic codes. So you will have to give r of x as the input, r of x, r1, r2 up to r suffix n minus k. So where r suffix n minus k. So the corresponding s0, s1, s2 up to s suffix n minus k, and the corresponding generator polynomials. So you can calculate the syndrome. So what is syndrome? Syndrome is nothing but it is r into h transpose. Syndrome is nothing but it is R into H transpose. That is what we are seeing here. It is more or less similar to operation of a linear block code. Okay. Now, if we look into this problem actually, see, find the code words. Okay. So find the code words if C of x, if m of x is given as 1 plus x power 2, and g of x is equal to 1 plus x plus x power 3. 1 plus x power 3 for a 7 comma 4 cyclic code. So we have n is equal to that is n comma 4. So as you have seen, n comma 4 means it is n comma k. So it is n comma k. So it is a 7 comma 4 cyclic code. So there are going to be 4 bits as input, and there are going to be 7 bits as output, number of information bits. Okay, 4 information bits, number of parity bits is nothing but there is r. So r is equal to n minus k is equal to 3. So the general representation is nothing but, so remainder of m of x into x power n minus k by g of x. So which is nothing but, so m of x into x power n minus k. Okay, so m of x into x power, so m of x is given as 1 plus x power 2, then x power n minus k, then x power n minus k is nothing but x power n minus k. So here the value of n is nothing but it is 7, and k is nothing but 4. So it's a 7 minus 4 is equal to 3. So x power 7 minus 4 is equal to 3. So x power 3 into 1 plus x square. Okay, so 1 plus x square, x power 3. So x power 3. So if you multiply 1 plus x power x square plus into x power 3, so this becomes x power 3. So x power 3 is written here. So x power 3 into x power 1. So x power 4. This is x power 4. Then if you multiply this x power 3 along with x power 2, it becomes along with x power 2. So it becomes what to say, x power 5. So you'll be having x power 5 plus x power 4 plus x power 3. Okay, and generator polynomial it is given as 1 plus x power 3. So 1 plus x power 3. So if you do the division operation, if you do the division operation here, so it comes to the remainder comes to x. Okay, so the remainder comes to x. So we have seen that Cp of x is nothing but the remainder. In the earlier slide we have seen that, see here, Cp of x is nothing but Cp of x is the remainder. Cp of x is the remainder from dividing m of x into x power n minus k by generator g of x. So this procedure which we are seen here, we are using it in the problem, and just trying to correlate. Okay, so this is what this remainder. So Cp of x comes to x. So this x is written here. So this Cp of x is written here. Then m of x into x power n minus k is the numerator. So x power 5 plus x power 4 plus x power 3. So x power 5 plus x power 4 plus x power 3. So this is the corresponding code word. So if you want to write the corresponding code word, so you can just write here. Okay, so the code words in the sense. mm, uh, so the code words in the sense, so if you want to calculate the code word, if you want to calculate the code word in the sense, what will be the corresponding code word? Probably I'll write the code word here. The code word, I'll write the corresponding code word here. So the code word is nothing but it is so writing from here, it is one. Okay, so this is actually x plus nothing. So 0, 1, 0, 1, 1, 1. So the corresponding code word. See here for this index, so it's actually 1 plus 1. So initially 1 is not there, so it is 0. So 0. So x power 1, so it is 1. X power 2 is not there, so it is x. Then x power 3 is 1, x power 4, x power 5. So this is the corresponding code word. So you can just find out code words correspondingly. So you can just find out the corresponding code words. So based on linearity property, or you can just find out by using cyclic property and so on. So the important thing is here is that this cyclic code word is more or less relevant to more or less relevant to the operation of linear block codes. The next such of code words will be the cyclic codes. So the cyclic codes and linear block codes go in hand with hand with each other. And okay, so the important thing of the cyclic codes is that, so the cyclic codes they follow. I mean, the cyclic codes they follow mainly the cyclic codes they mainly follow uh, linearity property. Cyclic codes they follow linearity property, which you need to be aware of. Cyclic codes uh, uh, okay, mainly linearity property, the properties of cyclic codes, linearity property and thing. So error correction and error detection, it is cyclic codes, it's nothing but it is a set of linear block codes. So it follows the properties. Main thing is that the properties are linearity property, and cyclic shift property. So based on these two properties, you can expect problems in you can expect problems in the competitive exams like GATE exams. So mainly these linear block codes and cyclic codes, they are mainly used for error detection and error correction. Okay, so they are used for actually error detection. They are mainly used for error detection and error correction. Error detection and error correction. Okay, so so you can so do work out the problems on linear block codes, and do work out problems on uh, cyclic codes, which we have seen as of now. So you'll be having linear block codes, cyclic codes, convolutional codes, whatever might be the type of codes. They are used for error correction and error detection. So